Start here. Today's functional group, ooh, where am I starting here? Is esters. Okay. Do you guys happen to have that slide of functional groups anywhere nearby? Remember what an ester is defined as? You can probably look later in this one here. Usually we write it something like this. R, C, O, O, R. And sometimes they write like R and then R prime. Is that what the one you have written looks like? Something like?
I think it's R, C, O, R.
Okay, well. Ethers or esters?
Esters. Esters is like all in one line, R, C to O, R prime, and then the C is double bonded to O.
Okay, well, this is what an ester looks like. Is this the picture you were describing?
Kind of.
Well, both of these are the same, only if we write it like the OO, it's kind of implied that one of the O's is actually like up here. So you might see this written as like a COO. This would be what we'd call an ester if you get a COO group in the middle of it. The dash just means that it goes to something on this side and on this side. Let me draw you some basic esters to begin with, actually. You need a C to an O to an O, and then both sides can keep going. So for example, you could have 3 carbons here, and you could have 2 carbons here. That's an ester. Or you could have another one there. Or another one.
So do we count as the oxygen part of the
I'll talk about how to name it in a second if you don't mind. Because this has a bit of a different naming scheme than we're used to. The point I want to make though is you could keep having carbons go in this direction for as long as you want. And you could actually have carbons go in this direction for as long as you want. You guys remember the term homologous? Basically it means that you can just keep adding another carbon. And esters are a good example of that. You can just keep adding carbons. In fact, these can actually loop back on themselves. You can have an ester as part of the middle of a cyclo. Let me see if I can draw one. You could go carbon to oxygen, and then this one can keep going. And this one could keep going. You could actually have an ester right here that looks like that. No. I mean, it does involve carbon and 2 oxygens, but it's not at all carbon dioxide, though. Carbon dioxide bonds like this, and just straight up stops, whereas this one actually keeps going. Okay. I'm going to talk about this slide in a bit here, I think. Actually, no, let me start with this. I want to start, before we talk about how to name them, I want to talk about how to make esters. Okay? And esters come from an esterification reaction, which is actually like a sub-type of reaction of what's called a condensation reaction. So let me show you an example of a typical condensation reaction. So I can make a diagram here. I'm going to have a molecule that goes like this, and it's going to have an O and an OH on it. And then here I'm going to put a molecule that's going to have like an H. And you know what? I think maybe I'm going to do a different one today than you guys are used to. We haven't talked about this particular functional group. I believe this is an amine. We don't cover them. But imagine that you had a molecule that looked like this and like this, and we react them together. Okay. A condensation reaction involves 2 molecules coming together, and out of the middle falls water. Can you guys see how OH and H, if I were to like rip that out of the middle, that would be a water molecule. And if I put these molecules together, you'd then have C, 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 O. But rather than having this little bit right here, you'd have to connect this to that. So then your nitrogen would come up over here, down to hydrogen, carbon, carbon, carbon. You visualize that?
Where's your water go?
Oh, well, plus water then. Okay. This is condensation. Condensation reactions are a very general term for anything where molecule 1 and molecule 2 come together, they react with each other, and a water falls out of the middle, and the other 2 pieces they loop together. Let me draw some more examples. So let's say we have these molecules here. Imagine that this OH could steal this H right here. You see how that could form a water? So like rip this out and then merge the rest of it together. So then the rest of it would be carbon, 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 and then it would have to attach itself to that O, to that C, to that O, to that C, to that C. Plus you'd have water.
And is this still condensation?
Okay, so that's the definition of condensation. So let me just go back up to the top there. Condensation reactions, a carboxylic acid combines with another reactant forming two products, one of which is an organic compound, and then the other one is water. Look at these two ones that I just did right here. Where were they? This right here was a carboxylic acid, and it reacted with something else. It made a combined product in water. Does that make sense? Or the lower one I had here. This right here would have been a carboxylic acid. It reacted with an alcohol, pull the water out, and so water is the reactant. General term, condensation. What we're going to talk about is a very specific type of condensation called esterification. So a condensation reaction just makes water. An esterification is a type of condensation that makes water, but it also makes an ester. Does that make sense? So that's the second definition here. They're very similar. This one here just makes an organic compound, and we don't know which one it makes. This one here specifically makes an ester. So let me show you an example of how to make an ester. Here's a carboxylic acid. What would we call this carboxylic acid? What's its name? Go for it. It would be known as ethanoic acid. Why ethanoic acid?
There's two carbons.
F. Ethanoic acid. Here's an alcohol. What would this alcohol be called? Methanol, because there's only one carbon here. If we were to combine these two things together, hopefully you can visualize, see how this OH right here and this H right here, I can rip them out, pull them out of the middle. Imagine that you're playing with like, I don't know, like Kinsey Ann's little Lego pieces, right? Rip one half of this one off, rip one half of this one off, and now put them together. Here you had a ship, here you had a car. I rip a few pieces off of this one and a few pieces off of this one, and now I have a ship car.
And water.
And water. Does that make sense? That's what's happening here. You're ripping this little bit out, and then you got to fit the rest of it together. If it looks like this, it's an ester. The question then is, how far on this side does it keep going? And how far on this side does it keep going? Because it could keep going further in both directions, depending on which chemicals you used. Since this one had 2 on this side, there's only 2 over here. Since this one had 1 on this side, there's 1 over here. But it is possible that this could keep extending in both directions.
So, in this case, is it like the alcohol? Is the alcohol right now just the other compound? That
Yeah,
you
the alcohol is the other organic compound. It has to, if it's going to make an ester, it has to be an alcohol.
Oh, okay.
Okay, so like if I drew back to the slide I just was on here, wherever I was drawing here. This reaction right here that I drew, see how this guy was a carboxylic acid?
Yeah.
This was not an alcohol.
So that's
It's-
just condensation.
Yeah, so it's not condensation, which is also esterification, it's just condensation. Whereas this one right here is condensation, which is esterification. It's like there's like an umbrella branch and then there's like a sub-branch. Cool.
Does it need a catalyst or does it just react?
Actually, it does need a catalyst. The catalyst required is typically H2SO4, and it also needs heat. Good question. I think that comes up later in my notes, but since you asked, let's write it here. H2SO4, sulfuric acid is required. And then you need some heat.
How do you know that?
I told you. I don't know. For a lot of these reactions, again, this is what makes organic kind of mean, is that for every reaction, you kind of have to know a catalyst for each reaction. So that's why we only do a few, so that hopefully you can just memorize them all. Yeah, sorry, I don't have a better answer than that. Okay, I'd like to talk now about how to name these things. And I'm going to give you a chart out of your data booklet. And we'll see whether maybe we can look at the compounds and figure out where the names came from. Okay. This compound right here is methyl butanoate. By the way, we're going to make these on Monday. Esters are known for their smells. Normally they're good smells though, because a lot of these are actually very nice smelling things. So, anyways. All right. So methyl butanoate. Let's see if we can figure out why it's called a methyl butanoate. Here is that OO group sitting right there, which really means that it's actually going up and then it's going over. Why is there a methyl to start? You're a methyl. Why is it a butanoate? Well, but refers to,
Wait, why is that one on?
Four.
There's 4 after.
because there's only one right here.
Yeah, but.
She's like, there's a methyl on the end too.
See how on this side right here there's a methyl group?
No, that's like I don't understand how
That's
that's
like one of the R's.
Because it's just a CH3. CH3 is methyl?
Yeah, but it's
Doesn't make
how
sense.
is that a branch?
Okay, good question here then. We don't really have trees in this particular sense anymore. We have like a hub, which is the double O's, and we have a branch that goes on one side of the hub and a branch that goes on the other side of the hub.
Everything relative to the COO.
Yes, that's a good way of putting it. In all of these molecules here, what I'm going to do is I'm going to circle the double O hub branch, and we're going to consider one direction, and we're going to consider the other direction, and see how far both of them go.
So that is it actually diamond? No. Like,
Okay, well, this right here is just a CH3 branch.
But
So this is a methyl, and then here you've got 4 in a row. That's where but comes. Give me a sec. Can I try over? Here's your hub. How many carbons do we have over here?
3, 2, 4.
oh, 5.
5. There's a little 4 right here. There's CH2 4 times plus an end cap, so there's 5. 5 is known as a pentyl. So on one side there's a group of 5, and on the other side there is 1. Don't forget this carbon right here. That counts. 1, 2, 3, 4. So that's where but comes from.
So go right side.
Connor Greer, can you please come to
I'll
the
talk about which
office?
side comes
Connor
first in a second,
Greer,
if you
please
don't
come
mind.
to the office.
Okay.
So it's always 08?
Yeah. So that the naming of a ester ends in 08. That's a good point. You'll notice that all of these end in the suffix 08.
Except for the last one.
Well, that's for the benzene.
Yeah, that one changes because of the benzene. But let's keep walking through them. Here is your hub in the middle. What do we have on this side right here? Well, I have 4 in a row. That's a butyl. But there's actually a branch on my branch. That's okay, we can work with that. So we'll call this a butyl, but then on the 1, 2, third one, this is like a methyl on a butyl. So that's why this side over here is a methyl butyl. Then on this side, there are 2 carbons, including the one that's part of this guy. So that's why it's called an ethanoate. Let me skip down. Let's do orange. Here's your hub. 2 O's. On this side over here, you've got 7 plus the end cap, so you've got 8. Hence the term octyl coming first. Then the question is, well, how many do you have on the other side of your hub, including the carbon that is there? 1 more, so then 2. So ethanoate. So like there's this one right here. Don't forget though, you do count this carbon as well.
So for like the 08 one, basically you just do it off the carbon that's like actually connected to the O.
Okay, so let's talk about those rules now here. The carbon that's actually connected to the oxygens, like the 2, because like what's really happening is you've got carbon, carbon, oxygen, oxygen, and then it keeps going. This is the second half of the word, and this is the first half of the word. The way you name these guys is in 2 parts. You name like the outside branch first, and then you name the inside branch. Let me try some more examples here.
Like I don't understand why that one's methyl and the other one gets the something.
Let me try another example here. This molecule right here, ugh, that was ugly. Let me try again here. This molecule right here will be known as ethyl butanoate. Let me see if I can try to explain why. See how this right here is kind of the main hub of the ester? So the ester is going to go in 2 directions. It's going to go left and it's going to go right. Okay. So first we got to figure out this branch right here. How many are there on that side of that branch? 2. Okay, so that's why it's known as an ethyl. Okay. Then on the other side, it keeps going the other way. Now this one is the one that actually gets priority. So the reason why this one gets to go with the O8 part is because this carbon right here is the one attached to both oxygens, whereas this carbon right here is just attached to just the one oxygen. So maybe it's better to think of this one as being a branch, and I guess this one right here is kind of like the main group, if you want to think of it that way. So then there's 1, 2, 3, 4. So this is the ethyl, this is the butanoate.
And it always produces water after.
And the other thing is that it'll make a water.
This is
In terms of knowing where this comes from, then, it always comes from an oic acid, and it always comes from an alcohol. So the oic acid would have looked like this. The alcohol would have looked like this. But I'm going to write the alcohol in like a reverse order so you can visualize it better. I'm going to write it as OH, CH2, CH3. You guys see how I'm just flipping it backwards? Hopefully you can visualize the OH from here and the O right here are going to fall out, which is where the C goes to this O and then keeps going. This is like the first half of the word, hence the ethyl, and this is the second half of the word, hence the bute. We just changed it to butanoate. That's how we knew it.
The other ones you changed it to why?
Back on these ones here.
Yeah.
Which one was butyl? Like this one right here?
Yeah.
Well, this one here was a bit of an exception here. You see how there's the 4 in a row right here?
Yeah.
Well, if we didn't have this guy right here, I would have just called this one butyl ethanoate. See how there's 4 right here? That would be butyl. And then there's 2 right here. That would make it eth. And then you just call it anoate. But this one was kind of screwy though because this branch right here had an extra branch off of it. We could name that. We just counted them and said 1, 2, 3 and said there is a 3-methyl on the butyl, and then the eth refers to there's 2 on the side.
So you put it in that order with like there's on the 3 there's this extra branch on the actual branch.
Yes.
So it would be alphabetical then.
No. That's why meth is before but this time.
Yeah.
If it was a butyl methyl, then it would be like a group of 1 within a branch of 4 off of it. Actually, that wouldn't even happen. That'd be a branch of 5 then.
How come all of the other ones end in O, A, T, E, but that one ends in Y?
This one has a common name for it.
Okay.
Because this one's kind of hard to name because of the benzene. You wouldn't be expected to know this one's name, just so you know. Let me try some more examples here. I'm going to draw these ones. Did I draw them on the next slide? No, I'll draw these ones out. Butanoic acid would be 1, 2, 3, 4 in a row. Then it would go up to O and over to OH. I usually find it best to draw the methanols like backwards, if that makes sense. So I'm going to write it as like C over to OH this way. I like to put them side by side so I can visualize how the water is going to fall out. I don't actually care which oxygen comes off, but both hydrogens are coming out and one of the oxygens. It doesn't really matter which one. No. So like for example, we're just going to rip all of that out. Since we're ripping out water, it's known as condensation. But this one right here is actually going to be more specific than condensation. It's actually going to be known as an esterification because it made an ester. So how do I name this guy? Well, there's 1 carbon on this side. So you start with methyl. And then there are 4 carbons right here. So then butanoate. So it's kind of different to name these guys because there's like 2 halves. It depends on how long each half goes for. Is this making more sense?
Where's the twist coming in?
What was that?
How is the twist coming in?
Actually, there really isn't a twist for this one so much.
You do benzene. Yeah, do we do the benzene?
Okay, well, let's try this one here.
Oh.
Let's do a benzene one, see how we can name it. So, we've got a propan-1-ol and a benzoic acid. So, first thing we gotta do is figure out how we're gonna draw benzoic acid. So, benzoic acid is gonna need to have a benzene. So, here's benzene. to make it an oic acid, we have to have a like that double bond OH thing here. Here's the problem. If I try to put it off of this carbon,
Too many bonds.
too many bonds. So benzoic acid does not look like this. It actually looks like this. You have your benzene. You go to an extra carbon, and then you have your.
Oh, I just draw it.
So this guy right here is benzoic acid.
Celine and AJ, can you please come to the office? Celine and AJ, please come to the office.
Okay. Then we want to write propane 1-ol, and I'm going to try to write it like in a backwards orientation. So I'm going to start with the OH right here, and then we need 3 carbons. I like it in the backwards orientation because I can visualize how water is falling out of this thing. So, bye-bye.
So we leave the O from the alcohol?
You got to leave one of the O's. I don't care which O you leave, but one of the O's stays behind. Doesn't matter which one.
Okay, how'd you go?
So just,
Alright, so what are we left with? Well, this molecule now looks like this. You got your benzene. It goes to the carbon and to the oxygen, like that. But then this OCCC sticks on the end, so it'll go OCCC. Okay, so good start there, Nicole. So this is where we start. We're going to call it a propyl. That's a propyl.
Oh, the double
And then now I have to name this thing right here. Well, it used to be benzoic acid, so we're going to call it benzoate. Remember how we were just changing everything to O8s? That's all you do is you just change it to O8. So this is a propyl, and then this used to be a benzene acid, so it just becomes propyl benzoate.
So it had to go in alphabetical order.
Like the
Yeah, but the
red.
benzoate acid one can't.
Okay, but like this is all part of the
Kevin
main
Cleaver,
thing
can you
here.
please come to the office?
And this is
Kevin
the branch
Cleaver,
hanging
please
off
come
of this
to the
side.
office.
This is the branch on this side right here. And then the benzoate is like the remaining part of it.
so it doesn't change the name of like benzene even though it's got that extra carbon jutting out?
It's the only way benzene works like that because like when I tried drawing this guy right here, there's too many bonds to make it work.
And it's not.
So it doesn't work.
Just plain old.
Technically there's actually 6 because there's not even there's a double bond kind of hidden in there too. So you'd have like 1, 2, 3, 4, 5, 6. So like that well breaks our rule. So the only way to do an oic acid on benzene is to throw an extra carbon on there.
So I mean, there's like 10 carbons then?
You'd have 1, 2, 3, 4, 5, 6, 7 carbons on this guy, and then 8, 9, 10. Yeah, you have 10 carbons total. This is basically what we just did, I guess, isn't it?
Yeah.
Yeah.
So again, hopefully you can visualize it. Take this, rip it out, shove that together. How do you name it? Start by naming this half of the. I don't know what analogy works best here. I like to think of this as like your hub. So first, figure out the outside branch of your ester. There's 3. Call it a propyl branch. Then you got to figure out the remaining part, including this carbon right here when you name it. So this right here was all known as a benzoic acid. So then change it to benzoate. Okay, let's go backwards. Let's say we made this ester. How do you know this is an ester? Yeah, you see this little bit right here? That's an ester. So first, let's draw this ester, and let's try to figure out how we could have made it. So, CH3, CH2, CH2, then C. So then the 2 O's means that one's going to have to go up, one's going to go over, and then keep going with the CH2, and cap it with the CH3. So, first question is, where is your hub? Well, it's right like here. So now we name like the outside branch, which is, there's 2 of them. So this will be an ethyl. And then we name like the main core part, including this carbon right here. The carbon that's attached to both oxygen is part of the name. So there's 1, 2, 3, plus the 4th one. So this will be known as a bute. And then you can change it to an O8, is the suffix for it.
I just have to remember the
Okay,
H
so
between the Oro to the.
I mentioned before, it's kind of like biology in a way, this unit, where it's less about, like, there's no math, obviously, right? It's more about memorizing naming schemes.
And the rules for each.
And the rules for each, and I mean, for every rule, there's like some different tweaks and exceptions. And okay, so let's answer the question though. Let's try to figure out how to like produce the ester. So let's go backwards. So in order to produce the ester, you would have needed 1, 2, 3, 4 in a row. OH. And then this guy right here would have needed the OH right there so that the water could fall out of the middle. So what were the two products required? Well, this right here was my oic acid. Good. So this would have been butanoic acid. And this would have been ethanol. Good. Make sense?
Stop.
Alright. Oh, let's do the same thing.
Methyl ethanol.
Name this ester, and let's figure out how we could have made it. After a while, you kind of pick up on it, don't you? So, I mean, let's go through all of it just to make sure I'm thorough. CH3 to C. Now, I mean, you'll note this C right here doesn't get any H's on it. That's a dead giveaway that it must then go to this O and to that O, and then the second O then keeps going. So in naming it, here's like your hub. This is a methyl right here. And then there's 2 right here, including the carbon that's like the right at the epicenter there. So ethanoate. After a while, you kind of figure out what these came from fairly quickly. The methyl must have come from methanol. And this must have come from ethanoic acid.
Oh yeah, you could just look at it.
After a while, you can kind of look at it and go, well, this part came from the alcohol, and this part came from the oic acid. Okay, so summary. I think we're done, right?
Yep.
Carboxylics end. Carboxylic acids always have to be on the end cap, so they're always capped with an H. We want to now remove that H. How are we going to remove that H? Well, we're going to need another OH from some sort of alcohol that keeps going so that we can remove this H and the OH and rip out a water. That's called condensation. If it makes an ester, it's condensation, which also happens to be esters. It's like saying we're all humans here, but some of us happen to be boys. That makes sense? It's like a subcategory. I don't know. Okay. So this is the main part of the ester. Hopefully you guys get what I was trying to suggest though is that this could keep going for I don't know how long. And this could keep going for I don't know how long. Those are the two parts of the word. This one right here is the first part of the word. This one right here is the second part of the word, and you change it to 08. That's how you name these things. You need sulfuric acid and heat as your catalyst.
That's it. Like
That's about it. So I mean, when I started at the beginning of the lesson saying you need to know how to name them, hopefully now you know how to name them. And then secondly, I need you to know how to make them. Okay. What we're going to do on Monday then is we're going to make some of these esters. And we're going to probably use most of the ones off of this list back here. If I wanted to make apple, what chemicals will I need to make apple? Well, I'm going to need methanol, and I would need butanoic acid.
That's just for the smell, or is that for like the legit apple, like
Well, this is like the synthesized smell of like an ester, fake smell, but it'll smell hopefully like apple.
So would that be like
Yes. Okay. So actually, before you guys take off, reasons why these are useful is in things like say perfume. The gum industry would be another good example. When you eat strawberry gum, are you actually eating gum that strawberries have been crammed into? Well, no, you're eating a chemical that has been flavored with a synthetic chemical that tastes like strawberries or like pineapple.
What's with the wintergreen one? The same.
if you want a banana, would you do like It would have to be like 2-methyl-butane.
Well, you need to have ethanoic acid,
Yeah. But then you would make.
and then you'd have to have like a butanol,
Right.
and you'd have to have a 3-methyl butanol.
Would you change it to 2 because it's shorter there?
Well, I think what you need to do is you need to have this with the OH on there, and then you'd have your CH3 right there. But by definition, this is priority. That makes sense. Okay. Okay. Any questions, or are you guys fairly good?
We're good.
Okay. Take a break. When you come back, you got 45 minutes to do stuff. I'd suggest either your lab or your assignment, because we're nearly done the unit now. Just one more set of notes, too. We did pretty good at getting through them all.
So, yeah,